Hello everyone, Assalamu alaikum. This is me, Aiza Freelancing Wali, and I'm a level 1 student at Rahat School, Islamabad campus. So, welcome back to the channel and today's session with Maya. So, let's start today our Maya. So, I'm connecting Maya with my stream. So, let's start. Please wait, viewers. I'm connecting.
Hi, what's up?
Hello Maya, today my topic is explain a cool physics concept in simple terms. So, are you ready for my conversation about this topic?
Sounds good. I'm definitely ready. What physical concept are you wanting to dive into first?
Okay, so first of all, please tell me what is the time dilation in simple words and how does speed affect time?
Okay, time dilation in simple terms. Basically, time passes differently for people depending on how fast they're moving relative to each other. It sounds weird, right? Think of it like this. Imagine you're on a spaceship, zooming super fast, let's say near the speed of light. To you on the ship, time feels normal. But to someone standing still on Earth watching you zoom by, your time would seem to slow down. So, a few hours for you on the spaceship might be years for the person on Earth. Speed is key here. The faster you go, the more significant the time difference becomes. At everyday speeds, we don't notice this effect because it's tiny. But as you approach the speed of light, which is incredibly fast, the effect gets really dramatic. Does that make sense as a starting point?
Okay, thank you so much, Maya, for your nice answer. So my next question is from you. Please tell me why does this time slow down in high speed and what happens to time near a black hole?
Okay, so why does time slow down at high speed? The physics behind it gets pretty dense, but the core idea is that space and time are actually connected. They're part of the same thing called spacetime. Einstein's theory of relativity says the speed of light in a vacuum is constant for everyone, no matter how fast they're moving. To maintain this constant speed, something has to give when you're going fast. That something is time. As you speed up, time stretches to keep the speed of light constant for you and for an outside observer. It's like if you're driving 60 amp hour and someone else is driving 30 amp hour, you both see light at the same speed, but your experience of time has to shift to make that true. Now, near a black hole, that's where things get really extreme. Black holes have insane gravity. It's so strong that it warps space time. The closer you get to a black hole, the more time slows down for you relative to someone farther away. And the closer you get, the slower time flows until theoretically, right at the event horizon, time stops altogether from an outside observer's perspective. From your perspective falling in, you'd experience time normally, but to the outside world, you appear to be frozen at the edge. It's really mind bending stuff.
Once
You
once
still
again.
there?
So Maya, my next question is from you. Please tell me who discovered time dilation and what is space time? Answer me, Maya. I'm waiting for your nice answer.
Albert Einstein discovered time dilation as part of his theory of special relativity in 1905. Initially, it wasn't really seen as something you'd notice in daily life, it was mostly a mathematical idea. Experiments in the decades after confirmed it, though, using atomic clocks on airplanes. So, space time, it's a bit of a concept, right? Imagine space is like a giant three-dimensional grid, like length, width, height. Now imagine time as another dimension we can't really visualize the same way. Einstein realized that space and time aren't separate things. They're interwoven into a four-dimensional fabric called space-time. Anything with mass bends this fabric. The marble bends it a little, the earth bends it more, and something really massive like a black hole bends it a lot. that bending is what we experience as gravity. So instead of thinking of gravity as a force pulling things down, think of objects following the curves in space-time caused by massive objects. Make sense? You still with me?
As very
Okay, it sounds like you're asking if humans can actually experience time dilation and if different people perceive time differently. Yes, to both. We actually experience time dilation constantly, but at speeds we move every day. The effect is far too small for us to notice. Astronauts on the International Space Station experience slight time dilation because of their speed relative to us on Earth. The effect is tiny. They age slightly slower than us by fractions of a second over months, but it's measurable with atomic clocks. We also experience a different kind of time dilation due to gravity. Someone at sea level ages slightly slower than someone living on a mountaintop because gravity is stronger at sea level. As for why people perceive time differently, that's more about psychology, not relativity. When you're intensely focused or having fun, time seems to fly by. When you're bored or waiting for something, it drags on. Our brains aren't perfect timekeepers. Memory and emotional state play a huge role in how we remember the passage of time. Your perception of time is subjective, while time dilation from relativity is measurable with precise instruments. Does that distinction help clarify it? Pretty good.
Thank you so much, Maya. My next question is from you. Please tell me what is twin paradox and how does gravity affect time? Does light speed relate to time?
Okay, let's tackle these. Green paradox is actually a bit of an economics concept, not physics. It suggests that policies promoting renewable energy might actually speed up fossil fuel consumption in the short term. Basically, if people think fossil fuels will become more expensive in the future because of climate regulations, they might burn through them faster now while they're cheaper. It's counterintuitive, right? Now, gravity and time. We talked about it earlier. Gravity affects time by warping space-time. The stronger the gravity, the slower time passes. Black holes demonstrate this the most drastically. As you get closer to a massive object like a planet or a black hole, gravity slows down time compared to someone farther away. As for light and time, they are super connected. Light always travels at the same speed for everyone, no matter their relative motion. This is a fundamental principle behind time dilation. Light's speed is constant, so time itself has to stretch or compress to keep that speed constant for all observers. Also, light takes time to travel. When we look at distant stars, we're seeing light that traveled for years or even millions of years to reach us. So, when we look at distant objects in space, we're actually looking back in time. Pretty wild when you think about it.
Okay, so my next question is from you. Please tell me, is time dilation real of the theoretical and how do scientists measure this dilation? Answer me, Maya.
Yeah, time dilation is absolutely real. It's not just theoretical. Scientists have measured it through several different experiments. For example, they've flown incredibly precise atomic clocks on airplanes. When they compared the clocks to identical clocks that stayed on the ground, the ones on the planes showed slightly less time passed. Not much, but measurable. They also tested it with highly accelerated particles. Particles in accelerators experience time dilation, and scientists can see their decay rate slow down relative to particles at rest. And like we talked about, the GPS system relies on accounting for both special and general relativistic effects. Otherwise, GPS wouldn't be accurate. Basically, scientists measure this dilation using incredibly precise atomic clocks and compare them in different situations at different speeds, heights, or gravitational potentials. The differences are tiny, but with atomic clock precision, they show up.
Okay,
Everything clicking
so
okay?
my next question is from you. Please tell me, does time stop at light speed and can I time to go backward? Answer me, Maya. I'm waiting for your nice answer.
Okay, good questions. If you could travel at the speed of light, which you actually can't because it would take infinite energy to accelerate something like with mass to that speed, then time would theoretically stop for you. From your perspective, you'd arrive somewhere instantaneously. But from someone standing still, it would still take however long it would normally take to cover the distance and going backwards in time. That's where things get much more theoretical. Some theories, like the idea of wormholes, suggest it might be possible in principle, but we have no idea if they actually exist or could be navigated. Importantly, most physicists think that backwards time travel would create paradoxes that could tear the fabric of causality itself. So, while the math suggests it might be possible in certain strange scenarios, there's no evidence it actually happens. At light speed, time would effectively stop, but backwards time travel remains firmly in science fiction for now.
Okay, so my next question is from you. Please tell me, why do clocks run slower in space? Answer me, Maya. I'm waiting for your nice answer.
Hey, Alex Wilson from YouTube. Clocks appear to turn slow in space because of two main effects related to Einstein's theories: special and general relativity. Special relativity says that time slows down as something moves faster. So, GPS satellites moving at high speed compared to us on Earth experience time a little slower. But the biggest effect comes from general relativity. The stronger gravity, the slower time passes. GPS satellites are farther from Earth's gravity than we are on the ground, so their clocks actually speed up slightly. To get accurate positioning, engineers have to correct for both of these effects. The satellite clocks are intentionally designed so they tick slightly faster when they're in orbit. When the satellite returns to Earth, time becomes normal with relative to the Earth. It's a really complex process, but it shows how relativity isn't just a theory. It has real world applications that affect technology we use every day.
Okay, so my next question is from you. Please tell me, how does GPS use time dilation and what happens to a giant in space, and can time dilation be seen in experiments? Answer me, Maya. I'm waiting for.
Okay, let's break these down. GPS systems actually depend on accounting for time dilation constantly. Satellites orbit at high speeds and experience less gravity than we do on the ground. Special relativity means their clocks would tick slower because of their speed, but general relativity means they'd tick faster because of weaker gravity. If engineers didn't correct for these time differences, about 38 microseconds per day, GPS would quickly become inaccurate, drifting off by miles per day. Next question: what happens to a giant in space? Well, time dilation affects everyone the same way, regardless of their size, so there wouldn't be any difference. Everyone experiences the same amount of time passing, regardless of whether they're large or small. Lastly, can time dilation be seen in experiments? Absolutely. There are super precise atomic clocks that get transported across countries on commercial airplanes that display measurable differences compared to clocks on Earth. Also, particle accelerators can shoot tiny particles very close to the speed of light, and scientists observe how their decay rates slow down because time dilation stretches out their lifespan. So, these effects aren't just theory, they've been repeatedly measured in actual experiments. You following okay?
Okay, so Maya, thank you so much for your answer. So please tell me what is relative speed and how does motion change time, and is this time the same everywhere? Answer me, Maya. I'm waiting for your answer.
I think you might have been asking about anesthetic sleep, is that right? I'm not entirely sure what you meant by anesthetic sleep, but to answer your questions, motion absolutely changes time, like we've been talking about. This is time dilation. The faster you move, the slower time passes for you compared to someone who's not moving. And as for sleep, yes, sleep occurs everywhere. Humans sleep and animals sleep everywhere. The human need for sleep remains the same, whether you're here on Earth, flying through space, or somewhere far from here.
Okay, so my next question is from you. Please tell me what happens to time instead as spaceship, and can time dilation affect daily life, and how fast do you need to go to notice the time dilation? Answer me.
Okay, this is getting a bit fragmented, but I'll try to piece this together. If you're on a spaceship traveling at very high speeds, time would pass slower for you compared to people on Earth. This is time dilation. You'd age slower. When you came back, you'd find that more time has passed on Earth than has passed for you. For things like daily life, that doesn't have an effect because you can't move fast enough to notice it. Can daily life be contained? Yes. Your daily routine, relationships, and responsibilities will stay with you wherever you go. It's about adapting your lifestyle and habits to a new context. And how do you need to go? I'm not sure what you're asking here. Do you mean how often someone would need to return home? That really depends on, personal needs and lifestyle goals. You decide how frequently you return based on your relationships, commitments, and what makes you feel connected.
Okay, so everything's okay, Maya. My next question is from you. Please, what is gravitational time dilation, and how does Earth gravity affect time? What is the speed of light?
All right, GOP. Gravitational time dilation is basically this: the stronger the gravity, the slower time passes. So, someone at sea level experiences time slightly slower than someone on a mountaintop because gravity is stronger at sea level. Earth's gravity does affect time. It slows down time relative to objects farther away from Earth's gravitational pull. Like clocks in orbit tick slightly faster than clocks on the ground, and the speed of light, that's fixed. It's approximately 299,792,458 meters per second, about 186,282 miles per second. It's an absolute constant in the universe. And this constancy is actually what makes time dilation possible in the first place. You still there, Geopay?
My next question is from you. Please tell me why cannot we feel time slowly, and how does time dilation affect space travel? Answer me, Maya. I'm waiting for your answer.
Okay. You're asking why we can't just make time slow down ourselves and how time dilation impacts space travel. So, we can't control time slowing down like hitting a pause button because time dilation isn't something we create. It's a natural consequence of the universe operating as it does. It happens because of how space and time are connected and how gravity works. We can experience the effects of time dilation by moving faster or being in different gravitational fields, but we can't intentionally manipulate it. As for space travel, time dilation is a big consideration. If you were to travel to a distant star at near light speed, time would pass much slower for you than on Earth. You could travel for what feels like a few years to you, but when you return to Earth, decades or even centuries could have passed. The faster and further you travel, the more significant this difference becomes. It's a practical challenge for long duration space missions and something future astronauts will need to account for.
My next question is from you. Please tell me, can time and dilation help in future travel? And what is the difference between space and time? Answer me, Maya.
You're asking about timeline direction and future travel, plus the difference between space and time. Okay, so there's no evidence that timeline direction or traveling backward in time is possible, but physicists debate different ideas all the time. The theoretical concept of wormholes could maybe allow for this, but it's purely theoretical and faces huge paradoxes. It's all really speculative, not something we can actually do. Now, space and time. Space is the three-dimensional extent we move through: up, down, left, right, forward, back. Time is usually thought of as a single direction we move along, from past to future. But Einstein's theory showed space and time aren't actually separate. They're woven together into something called spacetime. Gravity warps spacetime, affecting how we experience both space and time. Time travel could require manipulating spacetime somehow, which we just don't know how to do. Make sense?
Okay, so thank you so much. So, viewers of my Maya, thank you so much for watching. Allah Hafiz, Pakistan.